So thank you, Edgar. Thank you, Google. Thank everyone who came here. So it's a pleasure to visit IIST. So it's a pleasure to stay visiting Portugal, in special Coimbra. So here we're gonna talk about problems related to the Alt-Phillips functional. Okay, so we start with a variational problem of this pack of reboundary problems. Okay, so it's not working.
It's connection. Use the...
Yeah, okay, good.
Yeah, sorry. Of course it's not good.
By the way, okay, good, no problem. So, it's still not working this way. So,
Right now?
Okay.
This is see?
No, it's
So
not.
now
Okay.
here is
Yes. Okay, good. So I will start mention these two very nice papers. They are classical in the literature. So the first one is by Phillips. So in his PhD thesis in 1983, and the second one is in collaboration between Alt and Phillips in 1986. Okay, so they treat problems related to this functional. Okay, when in this case gamma is between 0 and 1. So in this range, it makes that functional to be non-differentiable. Okay, so we have a lot of issues, right, about this problem. Okay, so when you try to look at some equation or Lagrange equation associated to this problem, so we arrive at some kind of free boundary problem, you know, and as we see, we have Laplacian on the left-hand side, and we have a negative power of u on the right-hand side. So it means so you cannot have any PD information in the whole domain, you know. So when you are close to the free boundary, I mean the boundary of the positive set of the function, okay, so the right-hand side blows up. So this is one of the main issues about this problem. So it models density gases, and the single right-hand side means some rate of reaction, you know. If you try to, for example, to study the combustion of a gas, so when you arrive too close to the set when the density is small, is small, so you are losing some properties about the diffusion. So that's the problem in a physical context. Okay. And as I said, we don't know where the PDE is supposed to be satisfied. That's why we called a free boundary problem. Okay. And going back to some classical problems, the Alt-Phillips problem, it's a kind of interpolation of two relevant models. Okay, so the first one that I'd like to mention is the classical obstacle problem. So we have a huge literature about this problem. So this is the case when gamma is equal to 0. So as I said, we work in a range where the PDE is satisfied in a range between 0 and 1. In this case, we have obstacle problem, and in this range, at this point, at this value, so we get. Let me put everything here. Okay, we have the classical Bernoulli problem. So we have the zero-word term. Only having the characteristic function of u, okay, in the positive set. So if we talk about regularity results for that class of this class of problems, so we say that in the obstacle problem, solutions are locally C11, okay. So when you arrive here, so you have that solutions are C11. When we look at the Bernoulli problem, so it's more singular. That problem is more singular, and the solutions are only C01. Okay, so we have bounded gradient, for the Bernoulli problem, and we can move up, right, and conclude that the region is bounded when gamma is equal to 0, when we consider the obstacle problem. Okay, so as I mentioned, so okay, it interpolates. Okay, good. So what happens? What is happening when you consider the intermediate case? Okay, in this case, solutions are in fact C1 alpha. It's a sort of interpolation in terms of regularity too. So here we have C11, and here we have C01. Okay, so and between these things we have something like this. So solutions are C1, one alpha is equal to 1 minus gamma over 1 plus gamma. So look at, we have some continuity between the stream of this range. Okay, that's the idea. So this is shown by Phillips in 1983. Okay, so for nonlinear prototypes like P-Laplacian, so it's well known that the regularity is a minimum, right? So solutions are C1 alpha, when alpha is the minimum between some parameter less than alpha p, and 1 minus gamma over p minus 1 minus gamma. Okay, so this is like alpha p comes from the regularity theory for harmonic functions, p harmonic functions. Okay, I think I mentioned this. Okay, the third one is about p obstacle problem. So in a very nice paper by Anderson, Lindgren, and Chagolian in 2015, they proved that at the free boundary, solutions can be better than before, compared with Leitão-Terrois Queixeira. LQT, yeah, that's the right order. So in this case, they proved that solutions are in fact CP prime. I mean, P prime is some sort of the relation between P and the conjugate exponent. Okay, solutions are 1 plus 1 over P minus 1 at the free boundary. This is an unproved regularity. Okay, good. So, but what about the non-variational case? So if we consider in this case the full nonlinear operator on the left-hand side, so where F is uniformly elliptic in the viscosity sense, okay, we change the word that we are treating solutions right now. So this is proved that solutions are locally C1 alpha when alpha is exactly the same regularity obtained for the variational case when here we consider Laplacian one. Okay, so we can see F as a trace operator. Okay, that's the relationship between the non-variational and variational sense. Okay, that's the idea. So a paper together with Teixeira in 2013. So for the non-singular case, when gamma is negative, so we have no singularity on the right-hand side. So Teixeira proved that solutions are smoother than some range at free boundary points. Okay, so in a second paper, who in 2021 proved some sort of sharp estimate, right? Sharp Harnack inequality, where they proved in a consequence of that solutions that the free boundaries is C1 alpha. Okay, is C1 alpha for regular points. Regular points in the sense that we have some conditions on the density of the free boundary. Okay, okay.
It's non-variational. It's any solution to this problem.
Any solutions to this problem? Yes. So it's not any. So something, yes, further than that. So we consider in this case the limiting solution. So we perturb the solution, the problem, and we construct solutions, approximated solutions by Parano's method, and we take the limit. So we called, yeah, something like this. Yeah, something like this. Yes, yes. So yes, we changed the way to approach that problem, because in the variational sense we have minimizers. Okay, and you have to replace the way to consider solutions of the non-variational sense. So by approximating, perturbing the right-hand side, I will talk about this later. Okay, so the second thing, that we'd like to, yes. So here we consider some extremely important condition called uniformly ellipticity. Okay, so in this case, we prescribe how the diffusion is happening around the main directions. Okay, it's something like this. So we prescribe the minimal balance and the maximum balance of the diffusion on the left-hand side. So, and this is non-degenerate. Okay, I call that, in this case, we can remove that condition and make it a bit weaker than the before, and only consider degenerate operators like this. So satisfying some sort of monotonicity. Okay, so, and that's where we want to start to talk about. Okay, so I would like to forget about uniformly elliptic operators and start to think about degenerate ones. Okay, that's our main goal in this talk. Okay. Yes. What about to consider second order degenerate operators? Okay. So this is a work together our PhD student in João Pessoa, Ginaldo. So instead of consider the trace operator in a non-variational sense, we consider some operator given by the infinity Laplacian. Okay, this is our guide for today. So we consider solutions of this problem. Okay, in the positive set. So we have PDE where you have positivity of the solution. Okay, so good. So that's our problem. Okay, we consider the infinity Laplacian in this case, instead of any f in a fully nonlinear setting. So, and we keep our exponent between 0 and 1. Okay, so it's like our previous scenario about the variational case, because when gamma is 0, we connect it with the Bernoulli, the classical non-variational Bernoulli type problem, and when gamma is I'm sorry, when gamma is 0, we have obstacle problem. When gamma is equal to 1, we have the classical Bernoulli type problem, non-variational sense. Okay, non-variational sense. Good. So in this case, we consider the infinite Laplacian. Okay, but who is this guy? Right. So it's like, okay, we have a model trying to prescribe the behavior of the combustion of some gas, and we change the information. So we control in the first case when we have trace operator, we prescribe the minimum and maximum balance of the diffusion. So instead of this, I give you information about the diffusion only in direction of the gradient. So that's the difference of our model. Okay, that's what the infinite Laplacian does. Okay, so but it comes from a lot of motivations. So that's what I talked before. So this is elliptic only in the field of the gradient. Okay, it's like we look at the direction where the function grows faster, right? And you see what's happening with the diffusion process. That's the idea. Good. So when you look at the homogeneous problem case about the infinity harmonic functions, I mean, things like this, infinity Laplacian U equals 1. So we have a very classical literature behind that. So in this case, infinity harmonic functions are related with the problem about the best Lipschitz extension. Okay. So it's like, okay, we prescribe some data in the boundary with a Lipschitz norm, okay, and we try to extend inside the domain a function with exactly the same norm, Lipschitz norm, okay. So solutions, functions that satisfies these conditions are in fact infinity harmonic. So another way to think about infinity harmonic functions is when you consider the property of comparison with cones. Okay, this is another way to think about infinity harmonic functions. Good. But what about the regularity, even for the classical problem? So what about the regularity, local regularity for infinity harmonic functions? So it's easy to prove, for example, that infinity harmonic functions are local Lipschitz, okay? Solutions are local Lipschitz, even super or sub solutions. So if you have correlation, we can get almost arithmetically that solutions are in fact Lipschitz, okay? So it's easy to get Lipschitz, but something further is completely hard to get. Yes. Well, yes. Yes. It's yes. Thank you for giving the yes, because it's of course by the nature of the problem, right? Yes, exactly. So, but it's funny because it's a kind of problem that okay, we automatically we have this irregularity, but if you want to prove something further than that, as we're gonna see right now, we have that solutions are in fact 0, 1. So in 2012, right, Evans and Savy proved that solutions are only differentiable, right? So we know about the gradient, but we can't say nothing about the regularity of the gradient of solutions of infinity harmonic functions. So a bit later, in 2 dimensions, so Savin showed, a bit early, Savin showed in 2 dimensions that solutions are locally C1. So in 2 dimensions, using some spatial structure in the plane, so he could prove that solutions are I mean the gradient is in fact continuous. Okay, good. And Evans and Savin in 2008 proved that solutions are in fact C1 alpha. So they give for a small alpha that solution, the gradient is C0 alpha. That's the modulus of continuity of the gradient. Okay, so that's the scenario of regularity for infinity harmonic functions. So the open question is that, what about the optimal regularity for infinity harmonic functions? So by the Arson example, right, too long time. So the C1 alpha regularity, expected C1 alpha regularity cannot be better than C1 1/3. Cannot. So at most that exponent. Okay. So this is an open question. So what about the optimal regularity for this case? So it's also a conjecture that solutions are in fact C1 1/3. Okay. So solutions infinity harmonic functions are C1 1/3. So this is the magic number, 4/3. So, but it's still open. So it's a very, very hard problem to tackle. So that's only by mentioning the general theory about the infinite Laplacian. So, but our focus here is about to obtain analytic and geometric properties for viscosity solutions in some sense of that equation of this guy. Okay, so what about regularity for kind of okay? So we still keep the parameter between gamma, the singularity parameter between 0 and 1. Okay, so the case when gamma is equal to 0 was studied in Teixeira, Ross, and Urbano in 2015. So this is called, of course, as I mentioned, the infinity obstacle problem. Okay, so in this case, they proved that at free boundary points, solutions are C1 1/3 at free boundary points. Okay, so they consider some obstacle problem. I don't remember exactly what's the structure of the problem, but at free boundary, they could prove that solutions are better than expected, than we have in a general sense, even consider, for example, infinity harmonic functions. Okay, good. That's the result. And we here, in order to study this equation, we have to try to move around the lack of variational approach. Okay, so in fact here we have to make some sort of perturbation scheme, you know. So the idea is to add some term here, something like you consider, for example, the characteristic function 0 and 1, and you make it smooth, and you call this B, you know, and we define B epsilon by some adaptation of the previous one, assuming this. Okay, so this is a scaling invariant choice. Okay, so and we adapt to take the approximation of that singularity. Okay, so when epsilon goes to 0, it's like we are collapsing you are going to the classical characteristic function. You know, that's the idea. Okay, oh, that's the final picture when you plug together the approximation parameter. So it's like, okay, we add this, and okay, we let epsilon goes to 0, and the blue line goes to infinity in some sense, but it keeps having some giving some information in the whole domain. That's the point. Okay, so now we have some PD, right, in the whole domain. Okay, beta epsilon u like this. Okay, that's the idea. So it is considering whole B1. So in that case, we lose the characteristic of we have a free boundary, but it will have approximated PD in the whole domain. So now we consider solutions being the limiting a limiting function of approximated solutions. So here solutions of this guy we call U epsilon, you know, and in some sense we let epsilon to 0 and get some limiting solutions that by stability solves our original problem. Okay, that's the idea. So we fix a boundary data, okay, P, strictly greater than 0. So we can take it non-negative, okay? But I'd like to detach the solution being strictly positive. That's the idea, okay? And we let epsilon to 0, and we get the original problem. So, in this case, we use Perron's method to prove that solutions of the problem exist, right? And as I noted above, so we denote by U epsilon, okay? So they are positive if you fix the boundary datum positive too. And under a C01 compactness, we recover the original problem, okay, in the viscosity sense. That's our idea. So here, it comes for free. So we have Lipschitz regularity for free. Why? Because the right-hand side is non-negative. So as I mentioned, sub-solutions are C01. So the curious thing is that for example, Laplacian, we can't prove this kind of regularity for sub-solutions. So we have to manage further.
Minus.
Plus. Thank you, man. Thank you. Yes, this is plus. It has to be plus. You know exactly what I'm talking about. Yeah, because if you change the sign, you move the geometry of the solutions to and in this case, then you can't have free boundaries. Yes, because we have a different shape, you see, so we can't see the presence of free boundaries. Okay, forget about this the sign on the left right hand side or the left hand side. Okay, so plus. So as I misprint, yes. Thank you, Rodriguez. Good. So this is how our considering solutions in fact exist, and we prove that at free boundary in this rate. Okay, it's like here. So at this point we can see precisely okay, or maybe some distance of the free boundary. Okay, so and this is it can be given precisely as I put in on my slides. So theta is exactly equal to 4/3 plus gamma. Okay, 3 plus gamma. So you can look at differently than the trace case. I mean, the variational sense and non-variational sense for the trace. So the scenario changes a bit. So here, instead of this, we have that solutions are let me conclude this because I was forgetting about the not working. Hugo, help me, please.
Just use the mouse. Just use the mouse and click on the. Yeah, it's because I was.
Okay, good. Thank you. So solutions are C1, 1 minus gamma over 3 minus gamma. It's like this. So we have this. 3 plus gamma. That's the way how the Alt-Phillips, non-variational Alt-Phillips problem works with the infinite Laplacian case. Okay. So in this case, I think it's okay when you conclude that solutions that the free boundary at 3 boundary points, the gradient is 0, right? So someone asking? Okay. By Teixeira, Rossi, and Urbano. It's some kind of interpolation, continuous interpolation between the Bernoulli, and this is optimal. So we can give a precise radial example that concludes that that's the optimal exponent. Yes, when you look at gamma equals to 0, we get 1/3. Okay. Yes, that's one of our results, but it's our main result of this paper, of this project. Okay. So what is the idea for proving that result? So we have 2 main steps. The first step is we construct asymptotic estimates. So it's like, in the end, we prove that solution grows like everything less, a bit less than the optimal exponent. Okay, it's like we in the end prove that solutions grows like sup of u, c, r, and theta plus mu, where mu is less than 1. Okay, positive. That's our first step. So, and the second step is to move the asymptotic estimates to the optimal estimate. That's our main idea. So first step is that. So how do we prove, how we do manage with this kind of regularity result? So look at this. We don't have precisely the desired regularity, the desired inequality, but you have some sort of approximation of that thing. Because if you assume radius below from the value of u at a point x, so we can manage and have some similar estimate for approximated functions. Okay, good. So this is our main idea, the first main idea. So here we change a bit, and we make some sort of linearization of the solution of the problem, involving the infinite Laplacian. That's at first moment it was hard because it's hard to pick the optimal the original equation and move and prove that solutions of the corrective function by this guy solves this in the viscosity sense. So we make some sort of linearization because in a heuristic way, it's like if you want to prove that kind of graph, right? So it's like, okay, so if you pick u like this, and in the end we have some sort of linear behavior of that problem. So the idea is to take u, to transform u in that sense, and try to show that solutions are C0, 1 mu for any mu less than 1. That's our first idea. Using that, it solves that equation. Okay, it's quite it's not a clear equation, but it works in a relation with our singular problem. Okay, so in this case, f is given by b epsilon. Okay, so but in this case we can provide some sort of regularity result for any solution of this problem, putting here any L infinity function. Okay, that's our first idea. So that's the point. So we proved C01 minus estimates, regularity estimates for U gamma, and use Ishilion method for non-variational scenarios. So this is the replacement, trying to avoid the lack of rational approach for this case. Okay. Good. How do we prove that? So it's quite hard. It's a technical approach, but the idea is to look at the maximum point of that function, okay, phi. So this is a combination between a modulus of continuity, right, given exactly by mu, and the difference between the maximal points. I mean, that's the idea. So we have some additional terms, but I won't talk about these things. So it's only a technical procedure, right? So in this case, we assume that the maximum point is strictly greater than 0 at some interior part. So here we consider, for example, B1 across B1 for defining that function. And when you assume that by contradiction that condition, okay, so we are able to use the monotonicity coming from the Schillion lemma. Okay, so it's like here we have some sort of Hessian and gradient tilting at a point x, xm. And we have in this part the same for y, okay? And we can control this difference. So the good thing here is that instead of the trace, we have to manage with the structure of the infinity Laplacian. So that's why we have to consider the direction of the gradient acting on mx and my, okay? That's the idea. So, and we transform it, that inequality, that difference into some special ODE, okay, and it can be compared with this is the right hand side, okay, and you have some additional sign. This is the right. This side is right because you can have some sort of sign for this difference, and at this point we are able to conclude that the PDE related to this problem, look at this, because if you go back to the PDE, you know, so what is the PDE? Okay, good. Sorry, guys. Yes, this PDE, yes. Look at the PDE, we have this order, right? So we can put this additional information on the argument and conclude this. Conclude that we have that that this value is less than this one if you drop this exponent. So this is a contradiction when you look at this formation. You see? So because here this difference is greater than 0. So here we prove that we have this sign. So you get a contradiction, okay? So in that case, we change the sign, the sign of that expression in the interior of the B1. So and you can conclude that solutions are in fact C0 mu, right? That's in a general way the idea to prove the asymptotic irregularity for you at free boundary points, okay? Good. The second step, and the last one, is from asymptotic estimates, we'd like to imply that we have optimal oscillation decay, okay? Good. Let's do it. So we want to prove that. Okay, look at, if you notice, this is a more general version of our last result, because at free boundary points, we have exactly, this is some sort of Harnack inequality, okay, in the end. So this is what we want to prove for theta in our optimal way, okay, given by 4/3 plus gamma. Good. So how can we do that? So we assume by contradiction that we don't have any estimate like that. So for each integer kappa greater than 1, we construct our problem. We find epsilon kappa and u kappa, so that we have that the soup is greater than this part. Okay. So for some radial between 0.5, so, and x kappa in a interior of the B1. Okay. So, and we define our rescaled function like that, and we see that for that function, we solve the same problem, a singular problem, like a singular equation. So it's still on the same class of problem, okay? But we have some additional properties of that function, okay? So the super of that function is 1, and we control the point, the value of 0 at the phi kappa, and we control this part, you know. So in the end, phi kappa will solve some singular equation, where on the right hand side we have this part together, together our term called beta epsilon or b epsilon, d epsilon, okay. And in the end, we use the asymptotic irregularity to have that we are under compactness, okay? And we can let kappa, k goes to 0, and in the end we get some limit problem. Okay. We get some limited problem. Okay, no, I have to go back a bit. Yes, we get that limit problem. So in B1, so we have this product, okay? So in the end, I would like to use that this is infinity harmonic when phi 0 is positive, okay? So we get that solutions are infinity harmonic, where, yes, we have something like this. Here, right here. So at the free boundary, at this point, for example, we have that, okay, we use that the asymptotic estimate to prove that when this guy is 0, we can make some quotient here and conclude that the gradient of this guy at the free boundary is also 0. So you have some pack of information about phi 0 given by, okay, the simple of this guy is 1, and at 0 it's 0, and the gradient is also 0, okay? Exactly this, yes. The gradient is 0 at the free boundary points. So when you put together this pack of information, we have, okay, we have this. So we look at, so I'd like to use colors. No, it's fine. So let me change a bit. Yeah, here, right here. Good. So look at the free boundary, you know. So here the gradient is 0 for the limit function, and we pick some tangential ball, you know. So here we have that solutions are infinitely harmonic, okay? And at this point, we are able to use Alt-Phillips lemma for degenerate operators, including the infinity Laplacian. And we get that this quotient is strictly greater than 0. So it means that the gradient at free boundary points are greater than 0. Okay. So on the other hand, as we concluded before, so we look at this quotient, right? We get that this is 0. So that's why, that's where we prove, we get a contradiction and we prove the result. So this is one of the main ideas that I would like to talk for the audience. what we know here, Rodriguez, is that this project is 0. Yes, and we have some special free boundary condition that mean that no, I don't think so. We can manage with this. So this is so this is our limit point. So, well, our limit function. So I can't see any other information. Maybe it should be special in some sense. But for our purpose, it's enough to have this information. So in special that the gradient is 0 for me. That the most important information, right? Because it's like, okay, we have asymptotic, and the asymptotic goes to that formation, and we use half and get the contradiction. But
What is the equation for
PK? Good. Okay, PK. I would say that. So good. I got it. It will be some equation like that. So fit Laplacian U of phi k equals to the quotient of this guy. So sorry guys. So yes, this guy. So we have this. So we have B epsilon. We have phi. Okay, here is some bounded value here, and we have this. And here we have this ingredients here. So going to 0 right here, exactly these guys. And we put this guy on the other side. And we let this to 0. So okay, in the end, it's better than it's a bit different.
There is no oscillation. SK is always one sign, or SK is always positive or negative, or not? Because SK is what?
SK is positive, strictly positive.
Because you have the negative, the R is negative, and SK is negative. So this is
Yeah.
That's why this behaves wrong.
Very nice. So yes. So in the limit problem, so we get something further than, and yes, you're right. Agree. Local. Exactly. It's an obstacle problem. Oh, yeah.
That's nice.
Yeah. Yeah. Very nice. Nice remark.
Okay, then this is something.
Is in particular, yes. Good. Very nice. So come back to our ideas. So yes, so got a contradiction here, and okay, then so this is important, right? Constants do not depend on epsilon. Okay, do not depend on the infimum of the approximated functions. So I mean, then does not depend on the infimum of this guy, in some sense. So that's why we can go with the argument and can take the limit for that family, right? And we can recover our original estimate. Because if you look at I don't know if I wrote here, right? No, I didn't. So it's like, okay, we have the previous regularity result for something like this. Okay. Or yes, we proved that, right? this kind of Haneke inequality, optimal Haneke inequality. So at this point, it's like, okay, it is for U epsilon, okay? Sorry, this is for U epsilon. So, but when you let epsilon goes to 0, it's like, okay, we have that graph only for radio greater than this value, okay? That's the main difference. So it's not completely okay because we don't have any free boundary points for U epsilon. But if you assume that we have a free boundary for the limit problem or limit solution, so we can pass epsilon goes to 0, and we can have that the right hand side it's given explicitly in terms of the radius to theta. Okay, so that's the idea. So we call that something like floating oscillation estimates at floating level sets, because when you let epsilon goes to 0, you can tote the free boundary. Okay, that's our, well, that's the picture of the idea. Okay, so that's our main result. So we can prove a second result that it's called non-degeneracy estimates. So it's a kind of lower graph, lower estimates given exactly in terms of the optimal exponent. Okay, so yeah, we also prove this one. So we construct some super solution, and we put that super solution against our minimal Perron solution for each epsilon. That's the idea. So, and by minimality of the Perron solution, we can get some contradiction and prove that super VU is controlled from below by the same power of R. This is like we have some sort of total control on the solution. So given by bigger C here, you know, and small c here. So, and we trap the solution between these optimal contours. Okay, that's our second result. So we get a lot of consequence about the free boundary. For example, the free boundary is porosity. So you have some uniform density of the positive set. Okay, we can show that for each point. So at least some universal part of the free boundary is in the ball. Okay, so this is a geometric result. So okay, so I'd like to finish my 2 minutes. Okay, so this is our I talked about this result with Rafael or in Coimbra, and this is our result with Rafael and Vardan, and they are from Coimbra. Rafael is online. Rafa. So here we considered some sort of minimization problem, but it's in a different way. So instead of to consider, for example, the minimization problem of the Laplacian plus the negative power, oh, here is this, right? Gamma minus 1. So here we put some sort of obstacle condition. So in the end, we try to understand what's the behavior of the solution at free boundary points, at total points, at points like this, you know. So, and you prove that solution grows in an optimal way, right? Depending exactly on the behavior of, in terms of regularity, or depending on the behavior of the obstacle, and some gradients like P and dimension. We can prove something in a more general way. So it's a very nice result too. It's related with the variational case of Alt-Phillips functional, and the second one is the parabolic version of the singular fully nonlinear. This is in a uniform elliptic condition, okay, scenario. So we can provide that in X space, solutions are C1 alpha. One alpha is given in an optimal way. And in the time you have that solutions are C alpha over 2. Okay, so this is already submitted. So, okay. Muito obrigado